So let's start. Then we have Okay, yeah, thanks. Thank you for inviting me to give this talk. So I want to first start with the collaborators that are involved in this project. So there are a bunch of them. So Yuchen and NUS. Andre Grohr was actually an undergrad here. Haotian Jiang, Sanjeev Khanna, and Alan Sitford. So this talk is about submodular function minimization. This is a show of hands. How many have seen submodular functions before? So almost all of you. So just a quick reminder. So these are set functions. They are going to be defined over subsets of a universe of size capital N. I'm going to use capital N to denote the domain size. And the only property they have is this decreasing margin utility, which says if I have a subset S and I look at how much the function increases by this quantity, that increase has to be at least whatever that increases if I was added to a superset of this. Note that this increase could be negative. And in fact, for the problem that we're going to talk about, it's going to be only interesting if these things can possibly be negative. But that's what a submodular function is. And they arise everywhere, as many of you have probably seen them in some guise. So for example, the cut function of a graph or a hypergraph is a submodular function. So in particular, the universe is a set of vertices, and I take a subset of the vertices and look at how many edges cross this subset. Just that number, just that function is a submodular function. But they arise in various other places. For example, if I have a PSD matrix, semi-definite matrix, and I look at a subset of rows and columns, and look at this matrix and take determinant and log of that, that turns out to be a submodular. So they arise in many places, and in particular, many combinatorial optimization problems. And one paradigmatic problem is the following one. It just says, if I have just oracle access to the submodular function, I don't know, I don't tell you anything more, just that the function is submodular, and all you can do is ask for a subset and get its value. And what you want to find is the subset X with the A with the minimum possible value. So that's just unconstrained submodular function minimization. And in particular, this already captures questions like the minimum cut in a graph, minimum ST cut in a graph, directed graph, hypergraph. It also captures other combinatorial optimization problems, which are actually maximization ones. For example, the maximum matroid intersection problem, if you've heard of it, which itself generalizes bipartite matching, is also part of this bias duality. And many of course other functions which are submodular, the minimization problem is. So that's one reason to look at this problem. And the other reason, which hopefully, one thing that sort of leads us theorists to study this, is that it's extremely beautiful. So I'm going to talk a little bit about what is known. The whole talk is going to be about submodular function minimization, but I'll flash about what is known. But before that, a notation that I'll keep using. So I'm going to assume that the empty set evaluates to 0. That can be assumed because if I scale a submodular function additively, it remains submodular. So the minimum value that we are going to shoot for is going to be non-positive, could be negative. And I'm going to use capital M to denote the largest absolute value of this function. Now, of course, if I multiplicatively scale submodular function, it also remains submodular. So when you see this letter M, and you'll not see it very often, the assumption will be that the range is integer value. The range is going to be, if M makes sense if the range is integer value. And in that case, this is, so M is some sort of a scaling factor between the max and min. Okay. So it's a beautiful result. And it was known from the 80s that just using the property of submodularity is enough to find the minimum valued function, like this, the minimizer of submodular function, using only polynomially many queries for it. Yeah, so this, I'm finding something in this 2 to the n subsets using only polynomially many queries. And the essence of it is it actually, because of submodularity, this discrete optimization problem can be cast as a continuous convex optimization problem. Then you can just use ellipsoid algorithm or any other algorithm that is known, and that is enough to find this. So that's a one sentence reason for this. Of course, why that is true needs a little bit of proof, but it can be done if one had maybe in half an hour or 1 hour. Yes, this is Edmonds-Lowas extension, which takes us discrete submodular function to the continuous one, apply convex optimization techniques. And what you get is almost the best known result, right? So if you just use ellipsoid algorithm and you just care about query complexity, that's the only thing, and running time you don't even care about, then that already gives you an algorithm which makes n square queries, and there's a log, and there's a capital M dependence on this. M, remember, is the range of the function. And one could try to remove this M, and people have, and this is this paper of one of the co-authors in my papers, Haotian Jiang, just a few years back showed that you can get an n square log n for any submodular function independent of M, again using the ideas from ellipsoid cutting planes methods. But this algorithm is the number of queries that it makes is not efficient so far. So it's an exponential time algorithm because it has to solve the shortest lattice vector problem in this. It's a very nice result, but it's quadratic in n. Okay, so that's the thing. So the current best upper bound on this thing, this fact that you can do it in n square queries. That's quite fascinating if you're seeing this for the first time, that you can do it in n square queries. What about lower bounds? So the best, that's sort of the whole thing. We don't know very good lower bounds on this. The best lower bound before our work is the following due to Matt and actually everyone in Princeton, isn't it? They were all at that point in Princeton. Matt and others show that any deterministic algorithm, the modular function minimization algorithm, must make at least 2 times n queries. So just n is probably not that hard to show because you have to ask at least you have to touch every element somewhere. So n is not that hard, but 2n itself is non-trivial. Just to prove this is non-trivial. So that's the state of affairs. And I would like, maybe one motivation to give this talk is there a big gap between n square and n? It depends on who you ask. I think it is a big gap. I think one would like to settle this for such a fundamental problem. And maybe this is the reason to give this talk, to inspire some of you to start thinking about this. Okay, so one of the byproducts of what I'm going to talk today is actually we can do this slightly better now. We can say you need to make n log n, but it's still, we would like to know if the answer is n square or not. Okay. So the rest of the talk, or most of the rest of the talk, I'm going to talk about something slightly different. Instead of looking and focusing on the query complexity, we're going to look at focus on something else. And this is sort of been called parallel submodular function minimization. So this whole problem is a query access algorithm problem. You're querying some objects, you're getting some answer, and you're querying some more objects and getting some answer. So there's a notion of depth or parallelism or adaptivity. So a non-adaptive algorithm would make all the queries up front, get the answers, and return the object as the value. This is the minimizer. So that's a non-adaptive algorithm or a one-round algorithm. And more generally, you can define an R-round algorithm where the ith round's questions depends on the previous answers. And after R round of queries, you must tell me, right? So tell the solution. That's an R-round algorithm. And of course, we are only interested in algorithms which are efficient. So in every round, you're only making polynomially many queries. But now you can do n to the 3, n to the 4, n to the 100. But how shallow can you make your R? So that's the question. And so that's sort of connected to the notion of depth in parallel. So I should have mentioned before starting, I'm hoping this is a very informal thing. If there's any question, anytime, just raise your hand and ask. So any questions so far? So everything is clear? Good. So now, making a big leap and connecting to some P versus NC, one might think that something which can be done in polynomially many queries maybe can be done in polylogarithmic. So can you actually do this submodel function minimization in logarithmic or polylogarithmic depth, or that depth being that many rounds? Now, it's not too hard to show that you cannot do anything non-adaptively. One round, you need to query all the points, like almost all the points to the n. It's not a very hard thing to show. But even showing that 2 rounds you cannot do is quite a non-trivial. Okay, so unfortunately, there's bad news, as in bad news if you are an upper bound person. The answer is no, you cannot do logarithmic in many rounds. And indeed, this question was only as in studied recently. So in 2020, in this very nice paper, Eric Balkanski and Jan Singer showed that any algorithm must make omega log n by log n round. So it's still not does not rule out a logarithmic, but you cannot do it in 2-3 rounds. It's quite non-trivial paper, and that sort of inspired me and my co-authors to work on it. And we, yeah, so we are efficient means. Did you say efficient? Efficient is polynomially many queries per round. Any polynomial, yeah, and n to the 10,000 is also okay. And I'm not even caring about running. Good. So that's what efficient means. And in fact, one can actually go, okay, so let me say, so the result here is that this was brought to basically roughly cube root n rounds of queries. And then a little while later, we actually said, no, n rounds, roughly n rounds are needed. And the Jiang's algorithm, which runs in n square queries, runs in actually n log n rounds. So it's roughly the linear is the answer. And indeed, this algorithm at least, and maybe even this, and the actually efficient, you can take it to even 2 to the n to the 1 minus epsilon queries. What will change is the power of this log or something. Okay, so what my plan is to talk about these 2 results. So why am I talking about this, since this is stronger? And the reason is the dependence on, or the reason is this capital M. So remember, what is M? So if I talk about integer valued functions, M is the largest absolute value. So this lower bound, this is the one that I'll talk about in the beginning, in the first half, has actually low, like the maximum value is only capital M. It's a low range function. On the other hand, this one, the range is exponentially. Okay. Why does this matter? Well, for exact SFM, maybe you don't care. But in the end, I hope to tell one open problem that is bugging me is if I don't want exact, but approximate in some notion which I'll make clear, is that possible in low depth? So this actually gives us nothing for that because of this dependence on capital M. This gives us a very weak lower bound. That's going to be one thing that is. But for now, for the most of the technical part, I'm going to talk about exact. Okay, so that's about the introduction. I'm going to jump into these constructions. So any questions? Yes.
Do you know any lower bound for like a particular example?
So we'll come to that as well. I'm going to say a little bit in the last slide. The short answer is no. Not.
There plausibly any problem with
So let's ask this question after I describe this, and you'll see that this log n, if I do c, that's where the n to the c will come. But yeah, we can. Good. Okay. So both these results that I'm going to talk about, and in fact, even the Balkanski-Singer result, are basically the main technical idea is something called masking. Okay? So imagine the universe is, there's a partition of the universe that you don't know, that the algorithm designer doesn't know. And what you want to design, okay, and okay, so this is the partition that one doesn't know. The optimal solution somehow needs to get to that last bit. The order matters here. And the function is so designed, this is the meta argument, that in the first round, you don't know anything about the partition. And if you make poly n queries, you learn nothing else about the partition except maybe the first part. So I'm going to make this much partition of the universe. So the universe is capital N, subset of capital N elements. This is the partition of capital elements. Does that make sense? And we don't know the partition. And somehow all the action, until you get to this thing, you never will get the optimizer, a minimizer. And the function is so defined that this outer part, the P1 partition is sort of hiding information about P2 of PR. What does it mean? So if I make polynomially many queries in the first round, I learn nothing about this, but maybe the adversary completely gives me the P1, and then I recurse sort of after that. So I need to make R rounds to get to the action, where the action is. And that gives you a depth R lower bound. This is a very vague, very meta level argument, but that's the argument that has been used for some of these parallel lower bounds. And it is actually traced back to a work on parallel convex optimization, which is a very prescient and old paper of Nemirovsky from 1990. So sort of, you want to design a function where you get information in sort of rounds are needed, because the first round query sort of tells you nothing what is happening deeper in the. So this is vague, and we'll make this more precise in the various arguments. So let's sort of jump in. And one thing that as in the functions that we'll come up with, so there will be submodular functions, but they will not be like these min cut or something very natural functions. They will sort of tailored functions because they're lower bounds. So describing them is a little technical. So I'm hoping to sort of take you through this. Let's see how late can I lose you. So this is the game. I have a partition which is hidden. Now, given this partition, you can think of your submodular function of a special type, which we call partition submodular functions. So you should think of that whenever you query a subset, or given any subset of 1 to n is these black dots, it has a signature where basically, which is a r-dimensional integer vector, where xi basically says how many elements from part I did you pick. So we're going to look at, at least for the first construction, partition submodular functions, which basically are functions which are it's a f of s is some function of this integer vector x1 to xr. Okay? And basically, all you need from H is that it's concave in this sort of discrete concave function, that the marginal can only decrease if you have something large. Okay? So think of now submodular functions as concave functions on R dimensions, where, of course, if these were singletons, then I have really not gained anything. But think of R as small, but not too small. I want R large because that's the lower bound that I want. But that's the kind of function. Okay, so it's a function of how many pieces that you pick. Okay. Now, what we want to construct is a family of these partition functions. So I want to design this H. P will actually be a random equipartition. P is just to think of as a random equipartition. So this is the only randomness, and the randomness over this, when equipped with this H, gives me a family of submodular functions. Well, they have to be submodular. That's one thing that should be there. And I want the minima to be the last part. And this is the part that is interesting, that if you make I rounds of queries, then the algorithm should learn nothing about the parts P I plus 1 to R. And if that is the case, you get some momentum. So let me give a little more details. So what do I mean by this learn nothing? So again, P is a random equipartition. And so R pieces, each piece has n by R elements. H is fixed, which I want to construct with the following properties. So let's see. Let's look at the first round, right? If I look at the first round, when I query an S, almost surely, or with very high probability, the partitions will be, the signature of S will be almost the same, right? So how many pieces you take from part 1 will roughly be within how many pieces of part 2, up to how many pieces you take in part R, up to some standard deviations, up to square root small n, where small n is capital N by R. Okay? So that's what you're going to only query such things. If you make polynomially many queries, this is all you're going to query. And so what I would want is that for any such balanced X, my H should have the property that it's marginal right? How much you increase by is the same for every I except maybe the first part, because I'm willing to give you something about the first part. Otherwise, I'm going to tell you. And what this basically means is a random equipartition P1 to PR. And if I repartition P2 to PR to Q2 to QR, you basically won't be able to tell between these two. Okay, that's what I mean that I learned nothing about the partition except. So what we want to construct is an H where for balanced excess or roughly balanced excess, the marginals behave the same except for maybe the first coordinate. And more generally, after learning the first part, after learning I rounds, if I've played I minus 1 round, so the adversary has actually given me all the P1 to Pi minus 1. And I know they're useless. The gem is hidden in the last part. They'll probably not take anything, or you can do whatever. The algorithm designer can do whatever it wants. But on the remaining parts, it will be balanced. Exercise will be balanced. So I would want that the marginal of H for any J, it should be the same for any such thing. In particular, it should only depend on the size of X, which the algorithm designer anyway knew, and the other things, the prefix of X1 to Xi minus 1, which also the algorithm designer can choose because it knows the first I minus 1 parts. And this kind of a property is what we call suffix indistinguishability of H. So you want to construct an H, which basically on balanced excess does not reveal anything about the margin. Okay, so that's again, it's not the full definition, but it's sort of, hopefully I'm trying to give the inclination of what the challenges are. Okay, so let me now tell what the function looks like. Oh, okay, so sorry. So again, the framework, I want to consider two functions, H and H star. Again, each of them along with the random partition will give me two families of submodular functions. They have to be submodular. I want them both to be suffix indistinguishable. And H will be a function which is never negative. And H star will be a function which only if you take the last part is negative, right? So minimum of H star is negative, H is never negative. And in fact, for balanced X, you cannot distinguish them, Hx equal to H. So I want to construct such H's. Let me show you how this is done. So again, this is a partition, this is a signature. So Hx is simply the number of elements in X minus something, okay? Minus a function. And actually, I've written as a sum of two functions for a reason which hopefully will be clear. Okay, so Ax plus Bx. Before showing you what these functions are, I want to tell you what the properties I need from Ax. So what I want is that when all the xi's are small, so remember, for the balanced xi's, I should have the same behavior on the marginal for the derivative of A should not reveal anything. This derivative is 1 always. So when all the xi's are small, I want all the derivatives of A to be 0, all the derivatives of B to be 0. So basically, the A and B should not at all increase when xi's are small. Oh, and what that means is the derivative of H, so the cardinality will always increase when I add an element. So the derivative of H, how much the marginal is going to be plus 1. These will be 0. Which means when I take very few elements, H behaves as a linear function. It just keeps growing as I put in more elements. When all the xi's are small. When all the xi's are large, then I want the derivative of A to be 1 for every j. So when no matter what element I be, A should grow. But B skips a beat, right? So the B, for the first few elements, B does not increase if I add one more element. Anything from P2 to PR I add, B increases. The first one it leaves out. So in particular, that means that the derivative of the H function, this is always plus 1. This will be minus 1. And B will sometimes, most of the times, be minus 1, which will make the total derivative dj minus 1. So it means I'm going down. The H function, the value is going down, except on the first part where it does not go down. So in particular, if I take xi's are large, which I means I take a dense set and I just query the marginals for every element, this will just reveal itself and I get nothing else from there. So I'll pause here to just see if there are any questions. So I want to, this is the kind of construction we're doing. And I have two functions, and why am I doing this will probably make sense, a little more sense in the next. Okay, I want to construct these things. More generally, this was the first round. More generally, if I have an x which is, I said 0 here, but very, very small things and large things in the back, I again want a similar behavior from that point on. So all these points, the derivatives will be 0. So if I add anything, a does not increase, b does not increase. But whenever this is large, a increases and b sort of shifts by 1. And in particular, this is what is called like sort of, this is for any suffix dominated thing. But in particular, what I want is if everything is 0 and I have stuff here, a lot of stuff here, then a still increases. If I add an element, the a function should increase, b will not increase. So in particular, when I have this all, nothing I pick from here and here I keep picking stuff, this function never, the marginal of the total function never goes down. So if I pick anything here and I if I pick nothing from here and I keep only picking elements from here, the h function never becomes negative. It just goes up and then just plateaus. I say this because the only difference between h and h star, remember the h star function has to be negative, is in that last part. And that's the reason for this shift. In the last part, the h star function actually becomes negative after a certain. So if I picked nothing from here, I picked half the elements from here, the function kept increasing. H will plateau. H star after that will start getting negative. And if I choose that large correctly, it just becomes a little negative after a little. H star, that's the difference between H star and H. You'll only get to see only when you're picking 0 elements from here. And by the time you even get there, you've used up your R round on it. But H star and H only differ at that last thing. And that skipping a shift is why we needed like these two functions, A and B. Otherwise, we could have just kept one function. Okay, so again, this is hard to sort of convey without sort of trying to do the whole math. But I'm trying to give an idea so that once you read it, the paper, things will get more. Okay, so that's what we desire. Whether we can find such H's and A's and B's. So it turns out we can. This is how A looks like. Okay, so it's a mouthful. A says, so again, what do I want from A? If all the x's are small, A should not have any marginal when I add one element. And when all the x's are large, A should behave like, okay, it's like a linear function. So this is what it looks like. So I have some x. I look at the suffix sum. Okay, so x is like this. I look at the suffix sum, except I subtract some number tau from each part. Okay. Tau is roughly n over 2. It's actually n over 2 minus a few square root standard deviations. And here small n is the size of this. Okay. So what am I doing? So let me just give an example. So let's look at all x is all n. So basically I take everything. So I subtract roughly n over 2 from everything. So everything will give me n over 2. And I look at the largest such suffix sum. Of course, if everything is giving me n over 2, I should just go to the absolute left. And I'll get n over 2 for everything. So a of x is roughly n times r over 2, n over 2 r times. And nr is capital N, so it's roughly half the sum. On the other hand, if all the x's are small, like less than tau, I just wrote tau by 2, but less than tau, then all of these things will be negative, right? And it does not, so the max thing will be to take this thing or not take anything at all. Anyway, I'm taking the positive part of it. So I basically get ax equal to 0. So for ax to give me anything, some parts I need to take more than tau. And if I'm balanced, if I take more than tau anywhere, I'm taking more than tau everywhere. I'm sort of in this world, ax sort of does not reveal much. Okay. And this I've written here. So again, the function has to be defined everywhere. I cannot just define the function on balanced thing. Function has to be defined everywhere. And this I've written just to maybe show that if I take zeros everywhere and just n here, maybe as an example, what should ax be? Well, if I look at this suffix sum for anything other than here, I start getting negative things because 0 minus tau is minus tau. So I don't want negative things. So I'll move this j, the maximizer, we'll try to go as right as possible. It will go here, and there it will give me roughly. So it is a max over some sum, and then I take the positive. Okay. At this point, okay, so let me, that's A. And B, do I go to B already? Oh, no. So this is just saying that if all the x's are large, then A acts like just a linear function. So all the marginals are 1. If all the x's are small, then these are negative. And until I'm at the border, I don't cross anything. So every marginal is 0. So that's A. And B is just a shifted version where instead of taking a max, I look at the second max. So if I had all n's, A will be n over 2 because I'll just try to take the max here. B will have to skip this and start taking the max from here. And that's the shifted A in some. Okay, that's not the only thing that works. In fact, if in the paper we use A is the maximizer over odd elements, B is the maximizer over even elements, that also works. So that's the thing, and one can check. Yeah, one can check that it is this function is indeed suffix indistinguishable for the reasons that I've really lined out at a model level, but figure out what the tau is and etc. is. It's all not too difficult to. How much time do I have? Roughly half an hour. Oh, okay. Oh, I have more time. That's good to hear. So let me sort of say one point here. So the difference between H and H star was H star behaves differently on the last part, and tau was set, tau is that largeness thing, is set such that so tau was still now n by 2. But actually, if I have tau slightly less than n over 2, then as soon as I cross tau, I'll get -1, -1, -1. So I'll get basically this quantity becomes negative. I can choose my tau. So what I want to spend a little time, a little bit technical details, and maybe it's not fair, but I want to do it to show that how big can I make R? Because R, remember, this R here, number of pieces, is the lower bound on depth. Why can't I make it very big? And the reason is in the twiddles, right? So if I want to look at the restriction R, I have to sort of now open up what I meant by roughly balanced. So roughly balanced means x1, x2, x3 are allowed to deviate by some standard deviation, and the standard deviation is going to be square root of the small number n. Okay? So tau, I have to choose n over 2 minus some standard deviations away, like some c times standard deviation. And when you do that, now if I take all the elements, okay, so what is ax? Ax was, I look at how many more than tau elements I pick here, and I add them up for everything. Now I pick n by 2 plus c root n elements from everything. So when I sum them up, A's value becomes, well, nr by 2. That was the half of the whole set. But I have an extra term here, which is c root n for all of these r things. So A's value becomes cr root n, more than half of n, half of the total universe. B misses the first half because it's a second max. So B's value will be n by 2 plus cr root n minus the half of roughly the first half. Okay. Why am I saying this? Because if I evaluate H at the all n point, this thing is capital N. This is total number of elements. That cancels out this capital N by 2, capital N by 2. So what this evaluates to is roughly n by 2, small n by 2, minus r root n. This is the accumulation of standard deviation that is being, because I need to open up this also. The squiggle is up to some standard deviation. This is the accumulation of standard deviation r times, and this is what B leaves behind. Now H, I want it to be non-negative, right? It will be silly if the whole set is the minimizer for both H and H star. So H I want to be non-negative, and it's not hard to show that this is the minimizer in this case. And so if I just equate, I want this number to be non-negative. So R has to be square root of small n. Cannot be bigger than square root of small n, because otherwise this term will kill this term. And that gives a cube root capital N. So small n is the size of one part, If I look at R in terms of the whole universe, I get cube root capital. And that's a limit. As in this technique, we could not reach this. I say this because I mentioned this paper of Nemirovsky on parallel convex optimization, and he also proves a cube root n lower bound on parallel convex optimization. And the reason for the same is the same. The reason why the cube root n is we are stuck there, or maybe we are. Why these methods stop is the same. The standard deviation comes in. If there was no standard deviation, so care for that, we will be fine. We'll be getting better things, but we don't. So this method sort of matches at this roughly cube root n. You cannot prove a better bound using this, but it does prove cube root n. One thing that I have not talked about at all is why is this function submodular? So if I look at AX, I'll go and flash AX again a bit. It looks like this. It's max a soup of linear functions, and then I take a plus quantity. If you squint at it, it looks like a convex function. So minus AX is a concave function. So this you can convince is a concave function, and that's what H should be to become submodular. And indeed, this is not far from the truth. You can figure out and sit and check, and this is indeed submodular. You can do it. But what was very interesting for us, and this is not for the definition of max and second max, but odd max and even max, is actually this function is rank of a matroid plus rank 2 on a second matroid. So it's basically again, this is maybe only for the experts, but this is, there are two matroids where if I take the rank of this set S on the first matroid and rank of the complement of S on the second matroid, this sum is the same as Hx. And this is submodular. In fact, this is what appears in the duality of matroid intersection. And I know I'm being very fast, but the point that I wanted to make is that this construction actually not only implies lower bounds for parallel submodular function minimization, but you can ask for parallel matroid intersection, which is another problem which can be solved in polynomial time. Can you do it in low depth? So we cannot. Even if you have rank query access to matroids, you need cube root n depth to solve matroid intersection. Yeah, so this is one byproduct of this result. Yeah. So okay. So I'm being fast here. So matroid intersection is a maximization problem. I want to find set which is as large as possible, which is independent in both ways. If you cast it as that, if you look at the dual of this, it becomes to find a set S where the rank of the S in the first matroid plus the rank of the complement of S in the second matroid is minimized. So that duality is used, and that is a submodular function. So therefore, maximizing a matroid, the matroid intersection problem is a special case of submodular minimization. But you need that duality. Oh, no, yeah, it is the laminar. So A, you have to be odd and even, and the laminar matroids are P1, P1, P2, P3, P1, P2, P3, P5, the odd parts, and the other laminar matroid is from there to do the even. So it's they come from this partitions itself. Okay. Yeah.
That's like barely a.
Yeah, it's a chain matroid. It's a nested matroid. Yeah, it's perfect. Chain matroids are two chain matroids. So actually, one open problem is what is the upper bound for parallel matroid intersection, and it is known that there are sublinear bounds known. So I think it is best is, yeah, I'll not quote, but it's not n. You can beat n, but it's not smaller than root n yet. Okay, so the next 15 minutes, I would like to talk about the other lower bound. And this, the technique for this, again, the masking technique is the same, but the construction actually deviates completely from this partition. And in some sense, I feel this is a simpler lower bound, simpler idea. So I think this is easier to take home. but it suffers from this large range thing. And I want to at least show you why that large range. Okay. So this is the paper with Andre, Hautian, and Aaron. So we move away from partition submodular functions, but we don't move away from partitions. So again, we have a partition, and again, I want that in the first round, whatever queries you make, you get nothing from about and no knowledge about the P2 to PR. So this idea is the following. You basically think of this as a hidden box with a key, and the key is hidden in this set P1. Okay, so what do I mean? So K or K1 is a subset of P1, the random subset of P1 of roughly half the size. Okay, and now when you query a subset S of the whole universe, when an algo queries a set S, unless S intersect P1 is exactly this key, you learn nothing about P2 to PR. But if you are exactly key, I'll tell you, I'll open this box. Okay? So how do I, what's one way to do it? Let me just define f of s as the following. I look at the intersection with s intersect p1. If it is k1, then I call g a different function on the set restricted to p2 to pr. Okay, and how is g defined? G is defined recursively. Okay, so now if you don't query k1, you get 0. Otherwise, you get something. But now then you have to query exactly k2 in p2 and k3 in p3 and so on. And so rough, if I have what's the chance of a polynomial time algorithm to get this? Well, if this set size is bigger than some 2c log n, then it will n to the c algorithms won't work. So that gives you an n by 2c log n algorithm to find the minimizer in this kind of a function. A very simple idea. Yeah. Is the function that when and 0 everywhere else. Oh, so the problem is this function is not submodular. G is the same function recursively defined. So I think for a smaller, yeah. So I think I have it here. So G, so there is the hidden gold and the last thing. So and G on the last set is some submodular function, and F is defined like this. If you pick the key on the first set, the key on the second part, and the key on the last part, then finally I get G. Otherwise, you get big 0, right? And of course, okay. So this is not submodular. Okay, this is not submodular. Yeah. So it's but. So let's see why how we fix this. This is not submodular. Let's see why it is not submodular, and maybe then the fix will be here. So is this submodular? So let's see why it is not submodular. So okay. So this is the function. So fs just in the first layer, it's something and recursively defined on the remaining. B is the complement of A. A is the first part. So, okay, what is submodularity, right? It's saying that the marginal on a subset should be bigger than the marginal on a superset. And so let's just, know why I have so many animations. Okay, so let's look at a set, okay, an S set, where on the first part, I do pick the key. So S intersect A is the key. And say some S, I pick some arbitrary thing on the right-hand side. And T is a superset of S which exactly matches with S on the elements B. But on the first part, it is the whole part. Like T on intersect A is the whole. So what happens if I look at a marginal of an element E in T? Well, for T, since I don't pick the key, as in I've taken a superset, any superset I would do, I would pick the whole thing. But since I've not picked the key, both these things are 0. So I get 0 information. The marginal is 0. But S, well, S, this has passed. The marginal of E on S is whatever the marginal is on this G function. And I want this number to be bigger than this number. So the only way, this implies that G better be a monotone submodel. That's boring, right? So if G had any negative marginal, this is great. Okay. How do we fix this? We fix this by adding something to this simple looking function. This is what we call a submodularizer. Okay, so what do I need? So f is again this sort of locked function or like bunch of keys function, you can think of it, or at least just one key and the remaining. So what you do is you add a function phi to f, which has the property that if you pick a set S which matches the key on the first thing, phi does not do anything. Okay, it just keeps the sense of function. But if you pick any superset, this should be SA. I'm sorry. If you no, sorry, this is correct. So if I pick any superset of the key, like this T thing, then this submodularizer, this phi, has a big negative margin. Okay, so again, f, which is the function that is the key function, that adding an element f does not change the marginal, but phi will be so negative that I will have submodular, right? So on the set S which matches with the key, fs plus e minus fs is the marginal on that box. But when I don't pick the key, the submodularizer gives you a negative margin. And that negative marginal will, if you design this correctly, will be always smaller than this. That's the idea. Can you say that again? So key is
All of your parts are and
key
could be like a subset of,
it is n over 2, yes.
then the only key is supposed to be non-zero only on the contained exponentially small portion of that, which is what you're intending, right? Like the key of a modifier on an exponential function.
No. Phi is actually not going to be invisible, as in, so in most places, so unless you pick the key correctly, you'll only see sort of phi. And sets which don't contain the key or don't contain the key or are contained in the key, there I don't need anything. I'll just pass it. I'll just say 0 because there is no violation of submodularity there. But the things that are contained in key or contain the key, I have to add fudge. Yeah, man. So we have to do that as well. So yeah, I don't have the description of phi, I think, written here, but phi definitely looks at the cases where T contains K and T is contained in K, both places, exactly. Okay, so I don't have the full thing, but the full function looks like, again, the locked key function, just in the first layer, then recursively has to be, G is recursively defined, plus I add this submodularizer. Okay, now to make this submodularity go through, I do need this thing to be large, right? I need the ratio of this difference and this difference to be large because I could add n elements and S will not move at all, but T could move many times. Okay? And this ratio, this gap is what basically leads to the range of phi must be much larger than like n or n by n minus this, roughly n times larger than the range of G. And so when I recursively do it, the range becomes r times, the range becomes n raised to r. And if r is, I'm shooting for n by log n, the range becomes exponential. For an r round lower bound, I get an n to the r. So this leads to a range blow up, this idea, this sort of very nice, simple idea. But if you want to fix it this way, it leads to a range. Any questions? So I'm technical part is, I think, done. Okay, so yeah. Yes, so I'll come to approximate in one slide. The barrier is basically this. How do you define approximate? You define by saying the function is within some range and you want to be within epsilon f. But when the range is so large, when I bring it together, I don't really, there are so many things that could be approximate. I'll come to that in a second. Okay, so let me conclude, and we'll come to Chin's question in a bit. Okay, so this is the status. So what we could also show is just using the construction. Not only can we prove a lower bound on the depth, if you just look at a simple thing, and if I have time, I might even show you this. We can prove an n log n query lower bound, but only for deterministic algorithm. And I believe, okay, so a big open problem, of course, is can you prove anything superlinear? And a superlinear, I mean an n to the 1 plus c lower bound on the query complexity for SFM for any c. Or can it be that any submodular function can be minimized in O tilde n time? I think this will be a fascinating result, but I think this might be true. So I don't know. So that's one question. Now this is the thing, we only prove for deterministic, but I think you can also prove a randomized lower bound. If I have time, I would actually like to show this a bit in a bit, and maybe before we leave we can prove this. I don't know, maybe. So this seems doable. This will need some new idea. Now coming to approximate. So let's define what approximate SFM means. So in literature, it has been defined as follows. So I assume that the range, I'm no longer integer valued. I multiplicatively scale so that the range of my function is between -1 and 1. So remember, I'm keeping the f of empty set 0. That's one thing I've pinned. And I'm pinning down the multiplicative scale so that it's between -1 and 1. And now I'm allowed to deviate by additive epsilon. So opt is some negative number. And an epsilon approximate thing will allow to deviate by plus epsilon. Okay. So here is the question, what is the parallel complexity of epsilon approximate SFM? This I think is wide open. Since we have large, now I'll address your question, since we had a large range of like c to the n, when you shrink down, your basically numbers are like 1 by 2 to the n. Epsilon, should you think of it as a 0.001, is a huge number compared to that. And so it really does not prove any lower bound for approximate. In particular, for our construction, if you just return the whole set or something silly like that, is a epsilon approximate function. So it does not prove anything. However, the first construction, which has range n, does prove something. And I think this is the best lower bound we know, that you will, if you want an epsilon approximate, you need to make 1 by epsilon round. You cannot do it in 2 rounds or 3 rounds. And the best upper bound we know is that this is a follow-up paper that we had. This is an algorithm, like using parallel algorithms for convex optimization and connections with this lowest function. We could get a cube root n upper bound, but the dependence on epsilon is epsilon to the -2. So if you want a 0.001 approximate SFM, you can do it in cube root n rounds. Remember, you can't do exact, you need n by log n. But I don't know the answer to this question. Can this be made independent of n, or can there be a lower bound which has basically this? So this we have tried for quite a while, and we don't have. This is the gap. As in, there could be an order 1 by epsilon round algorithm which makes poly n queries. Number of queries is still poly n every round, but the depth could be order 1 over epsilon. That's possible.
What if some other function is on this that
Special functions in the next slide. We'll come to that. Yeah. So for cut functions, 1 round, I can learn the whole graph.
So this is about query complex.
Query complex.
There were words.
We don't know. So short answer is the things I'm aware of don't give anything much. But yeah, those are all interesting questions. So communication, you have to cast the question correctly. Like Alice has a submodular function, Bob has a more. So there are some results there, but they're positive. They're positive rather than negative. No, they're positive results in communication. As in if you cast it this way. But that doesn't mean we cannot cast it in a different way and get some work. But I don't know of any lower bound. This is the gap that I am aware. So special cases. So so this is a special case that many people, including people in this room, have worked on. So what can I say if instead of a general submodular function, I'm looking at cut functions on graphs on n words? Okay, so if I'm looking at cut functions on graphs, then the round complexity is very simple because I can learn the graph in n choose 2 queries. I can query for every pair of nodes, 3 queries are needed to figure out if there's an edge or not. And once I know the graph, I can do whatever I want. So that's a little boring. But what is a query complexity? People have tried to understand this. So there's something quite interesting is known. So in fact, so the first paper was, this is not Rubinfeld, this is Rubinstein. I'm sorry. So Matt, Salil, and Aviad had this very nice paper, ITCS 2018, asking this basically this question, and they gave an n polylog n query algorithm on simple undirected graph. Simple being there are no weights allowed. So I could have a weighted graph and the cut function is still submod. And then a follow-up paper actually gave an order n. There is no logs needed. And it's a Monte Carlo randomized algorithm to find the minimum cut in any undirected simple graph. That's pretty nice. If I have weights, the function is still submodular. The best thing I think is still n polylog n, and this is a follow-up paper to Matt's paper by Shagni Mukhopad and Nanongkai, and answer is n polylog n. Okay? All of these are randomized. You can look at st-min cut. St-min cut is another submodular function. There, the gap is actually bigger, as in best. So Matt and colleagues gave an n to the 5/3 query algorithm. Again, simple and randomized. This was recently de-randomized. Actually, it's not fair to call it de-randomized. They gave a deterministic algorithm. This is a paper that will appear in SODA 2025, having the same complexity. It's interesting that the same complexity by 2 different methods. So, the open question is, can you get this down to 4 tilde n? As in, I don't know, I have not worked on st-min cut, so I don't know what to think of it. But if you can prove a lower bound, that would be great. Will be happy for some modular functions. But we don't know. These are for undirected. Directed, we don't know anything like this. Like quadratic is where we are stuck at. Basically learning the graph kind of idea. So anything subquadratic will be fascinating, the directed graph. People are looking for open problems. This is a very nice problem, and or find a way to prove a lower bound using any technique. So, yeah. People have actually, yes, it does make sense. Yeah, so hypergraph, I can tell you. So, I don't think there are any. Okay, so hypergraph. So, if you just ask the question of not finding the min cut, but tell me if the graph is connected or not, then also people have looked. In fact, my student is looking at that problem, and there we can give order n for weighted graphs, and for hypergraphs, order n log n follows from that. But min cut in hypergraphs, I think, is open. Order n square is the best. So that's also, and it will be nice to see the relationship between directed graphs and hypergraphs. I don't know.
So,
Yeah.
you may have bound the number of edges.
Yeah. It does. You can learn the whole graph in roughly order m queries.
So the reason I'm asking is, in the white box where you could sparsify the
Yes. So these. So again, this is also there in Matt's paper. So this is a prescient paper from 2018. They do the sparsification. They do approximate problem. I don't think the same thing has been answered for hypergraphs yet, although I don't know.
very good. Very good.
Correct, but do they work in the cut query model? Maybe they do. This is the thing, as in that if one can check that, then we have that, and I believe they might. I don't know. Don't quote me on this, but that possibly will fall. Maybe Matt, you know something already.
Regular very simple, like spectral stuff.
The combinatorial
But there are for hypergraph, there has been very recent nice works which don't go via spectral. So, correct. So that it's not just that, I think. It's not just that. So it's a good question. Okay. Yeah, so let me end there. Thank you. Again, if there's time, I can look at the n-log n puzzle. I throw out a puzzle. Is that, or I can also. Yeah. So I can also leave. I want to extend hospitality.